This conference will now be recorded.
Okay, good morning, everyone. Sorry for the late notice on my emails for this meeting. Got a little bit carried away with a long weekend myself. So, today I wanted to give. I've made some progress in discussions with various people on some of my original concepts. It feels like it seems to be getting a little bit more solid now, so I wanted to give an update on that. I wanted to touch on the OCP Global Summit. I think as of today, this is the first day of the opening for the call for papers. So we want to maybe just see what we want to do there. And on the white paper, I just wanted to make a little bit more progress there. I think there's some actions that we can start to get rolling on. I've got some discussions going with people, so I'm going to be pasting some pieces in to get other people rolling. So using the white paper to try and get some parallel activities going on, so to speak. So maybe we can get some actions in the white paper, so we can actually start to get some progress there. Let me just check. I can hear people popping in here. So morning Darwish and morning Hisham. Let me just update.
Good morning, Alan.
Good morning. Hisham, is this your first time or have you been on before?
No, I have been here before.
You have? Sorry.
Yeah. When you were discussing the agenda for the workshop.
Yes. My apologies. Yeah, I got you. So, Al Wegner, can you talk? Can you come off mute and say hi? Are you there? I mean, you're new, Al, so not to me, but to everybody else. Okay, he's being shy. That's very unlike Al. Okay, Al, if you could hear us and you come online, it'd be nice to give a quick introduction of yourself and what your company does and your interest in this work group. So we'll come back to that, or I'll get some words from Al to paste in later. Okay, so I'm going to move on to the latest update. Like I said in my concepts. So let's progress to that now. If I go into my okay, can everybody see that? You should see OCP hPC.
Yeah, we can see it.
Good. Okay, so like I said, I've been working with a few outside people on some various concepts, on updating the concepts and taking feedback on what we've done already. So some large companies and small companies, and so this is a little bit of an update on where my head's at least, towards where we're going in this work group. So what I did is I took an example in terms of technology that already exists today, and saying how would this fit into our hPC. How would this particular processor fit into our hPC world? And I guess AMD are leading the world, certainly on the CPU side of things right now. And so this is a nice little. This is the EPYC Rome I/O die, or the Rome CPU, and in the middle is the I/O die, which is in particular what we're interested in. It connects to the outside world where our system level architecture comes into play. So you can see that they've got separate. This is a chiplet world, so it sort of links to the ODSA as well. The work group in OCP is working on chiplets. And obviously this could have HBMs and everything else in it, but this is just taking this snapshot of this particular type of processor and how would it fit into our architecture is really where I'm trying to go here. Just a moment, I've got notes on. Okay. Oh, great, thanks, Luke. So this is the way this one's laid out. I know I've lost my mouse. There we go. But it doesn't take beyond the wit of man to think that actually they could update those individual dies to accelerators or mix and match accelerators and CPUs. And I'm not sure if they do it at the moment, but you know, they're requiring Xilinx. They could put Xilinx FPGAs down, or obviously AMD GPUs they could put down, and maybe even AI dies. So this is a potential mix and match approach here, which is quite interesting. If we take
Alan, I have a question.
Yeah,
since
sure.
Now lots of packet processing is done by virtualized components in data center, so packet can get into Ingress interface and then get processed by various components which runs on CPUs or GPUs, and maybe CPUs or GPUs, and then goes to the egress. So computing and communication are really coming together now.
Yes, exactly. Yes.
Yeah. So what happens when we're talking about high performance computing, but that is actually related to high performance communication.
Right.
So as one of the concepts we are going to discuss in this group is the relationship between high performance computing and high performance communication.
Yes, and well, so again, if you roll back through our previous discussions before you joined, really we're obviously at the open hardware piece of the equation here, in terms of, and we're trying to build a modular approach to constructing HPC computing platforms. Whereas they've been traditionally, HPC has been very open except for the hardware, you know, very, very custom machines at the very high end from the likes of Cray and Silicon Graphics, etc. So this is, we're focusing on the hardware side. So communication is a huge part, and actually one of the key drivers we started with early on is a lot of the time historically it's all been about compute, but it is much more about the data now. And actually, you need the data and compute really tightly coupled, because moving exabytes of data around takes longer to move the data to the compute than to actually run the job. So I would ask if you maybe take a look at that, or hopefully some of this will come through in this presentation. But yeah, we're trying to look holistically at the system level of how can we bring the innovation that's going on at the silicon level, both in the processors, accelerators, and storage, and media, and memory, and obviously hook them together very efficiently. So yes, that's a piece of the pie we're looking at here.
Thank you very much. That's good. That's good.
Okay, good. So on that note, if you look, this is the Rome IO die, which has been in production for a while, and you can see that the die layout, and there's a lot of IO on here. I don't want to spend too much time on this, but I just highlighted in yellow the 8 DDR4 memory channels on the Rome IO die. And if you listen to the chiplet world, you know, beachfront is critical, and certainly in area as well, of how much area do you consume for your controller. You're getting about 3 gigabytes per second per millimeter squared of memory controller. So if you listen to the rumors, the WikiLeaks, so to speak, of our industry, this is the guess of what's going on with the EPYC Genoa IO die. I don't know if it's particularly correct or not, but I've just taken out of what's out there, and they're moving towards 12 DDR5 channels allegedly, and the Infinity fabrics again allegedly it looks like they're going up to 12 of those channels as well. So I've basically written down the aggregate bandwidths, read plus write, of everything that's going on. 128 lanes of PCIe Gen 5, DDR5, you know, 500 gigabytes per second of memory bandwidth, and fabric, Infinity fabric, 1.5 terabytes of Infinity fabric, potentially, with a question mark, I don't know, and a terabyte per second of CXL stroke PCI bandwidth, potentially. If we look at the memory bandwidth, on the other hand, even with this major upgrade, if this is what's happened, this is supposed to be launched in 2023. This Genoa IO die, I believe. But if you look at the fabric, your memory is oversubscribed 3 times to the Infinity Fabric, 2 times to the PCI, or 5 times oversubscribed if you put Fabric and PCI together. So we can see that this parallel memory bus is becoming a problem in terms of consuming too much real estate and not giving enough bandwidth for I/O. To your point, Hisham. So, and also just on the memory capacity side, DDR5 DIMMs can go up to 256 gigabytes. I doubt they do now, but eventually, so you could get about 3 terabytes of attached memory to this. So obviously far bigger than HBM, but far slower than HBM. But I think we can now safely say that memory is finally going serial. I think we're going to make it this time. After many failed attempts over the last decade, I think we're going to make it. And so to that point, the DDR DIMM is a parallel interface. It's woefully uncomposable, but everything else has gone serial. The open memory interface was the first to take this format, so to speak, and actually take it to a transceiver attached with a very low latency, and that's the OMI DDIMM format within JEDEC. Last year, as I was putting these concepts together, I was saying, hey, it would be really good if we could have an OMI in an E3.S format, and you could get 2 OMI channels in the E3.S format with the 16 lanes. So proposed that in 2020. Smart Modular actually were quite well ahead of the game as well in Gen Z, and they actually made an FPGA based DRAM module in 2020. And so that was FPGA. So that actually can talk multi-protocol, but they've just implemented Gen Z. Also, Samsung have just announced, as I think we briefly discussed in the last call, their CXL.mem in E3 format. And my guess, my hunch is that that's an FPGA buffer there for I can't believe that's an ASIC yet for the CXL world, but that's just my hunch. And the OMI one, we could actually use the current buffers from Microchip, or we could do an FPGA one as well. So if the Samsung and Smart are both FPGAs, it would be very easy to implement OMI in either of those ones as well. So I think that we are beginning to make the leap. And it looks like, I think this E3 format is actually, because it's sort of a serviceable format, and I think it may actually be better because it brings storage and memory closer together in this new format. So I think that's very attractive, which was again driven by Gen Z.
Are you going, Alan, to look at in-memory computing?
Right. Yeah. Well, so the in-memory was also a piece of this. One of my arguments is we've been doing in-memory computing for the last decade, really, or more. Because if you take a CPU, more than half of it is cache memory or management of the cache memory to feed the CPU cores. So really, that is already a PIM. An FPGA arguably has been a PIM forever in my mind. You know, it's the way it formats the memory. So yeah, but there are more exotic PIMs going on, and there's some AI chips with lots of memory on board, like graph cores. So I think it's a bit of a blurring of in-memory. And I think with this die stacking with like logic dies at the bottom next to media dies, the lines are being blurred anyway. And so I don't really look at it. I just think we've been living in a PIM world anyway, to a greater or lesser extent. So, but that's one piece of this equation. So what we did here, or what I did here, is I took the area of the OMI memory controller, which is available, and in the same beachfront, and it's critical to see here, beachfront of the DDR channels, we can fit 24 OMI channels. And with the DDR5 going to 12, I can only assume they're going 3 deep with the DDR5. And the pink you can see hanging out there is a DDR4 from the Rome Epic Rome IO die. So actually, we're saving chip area on this memory IO. and we're getting more channels, and we've got more bandwidth. So we've actually upped the memory bandwidth to this die. If this is a concept, obviously, I'd love AMD to do this, but it's a concept. So we up the memory bandwidth to 1.5 terabytes per second on this same physical die here, and that I understand the shrink is to a 7 nanometer. So then the memory becomes much more balanced. It's actually full-blown one-to-one with the Infinity Fabric, if that's the right number for the Infinity Fabric. It's actually undersubscribed. There's memory bandwidth left over if you look at it from a PCI CXL perspective, and it's just slightly oversubscribed on both of them, which, you know, people that would talk, you know, you don't need all the bandwidth all the time. So this is a great improvement on the previous ones with the parallel memory. Equally, the memory capacity there is of the order of 6 terabytes, so twice the amount of what you can get on DDR5 as proposed going forward. Again, if you've got the devices. So this means we've now launched, you know, so hypothetically we've launched ourselves into this. Everything's transceiver, everything's composable, and I went in the wrong direction. Oh yes, on this you can have simultaneous low latency near memory with the OMI channel at least, and you could sorry, don't move slides. And you could also, that same memory could serve through the CXL PCI bus as CXL.mem. So you can actually share through this, as well as being low latency to the primary processors on the Infinity Fabric, and a CXL memory to everyone else. So you don't have a stranded pool of memory. Everything is shareable. Will be the key thing here. So this is, again, this is only one way to skin the cat. I'm just taking AMD's EPIC die and saying, look, this is where our industry could go. I think there may be some protocol tweaks we needed to do on CXL to make this work, but from what I've been told, but this is looked like an interesting direction. So, I mean, really what we're saying here is if we added OMI to it, and by the way, this doesn't preclude others, but just the OMI is the analysis. Balanced memory bandwidth to Infinity Fabric and PCI bandwidth, so that's what we said earlier. You'd actually reduce the socket size. There was talk about the socket being huge, 6,000 pin socket. You'd actually reduce it to, or keep it the same as the current EPIC Rome socket, or even smaller, because you actually save about, you've got about a quarter of the pins. So 24 OMI channels take up the space of 6 DDR channels. And that would be, I'm guessing that would be similar for CXL or Gen Z. Far easier motherboard routing as a result, fewer layers and lower cost if you do that. Memory becomes composable with SerDes, as I've mentioned, and also suddenly now you've gone to this agnostic memory interface. You can connect all sorts of types of memory. And I've just said it as an example, LPDDR5 could go behind OMI, Gen Z, or CXL for improved power and better random access. And we can also put HBM behind it, and that's an interesting thing if you did want to disaggregate the HBM. So now we've got this. Now we've converted our hypothetical AMD Genoa CPU into all transceiver attached. We can now actually make this HPC module block diagram. So I'm showing it in the connector format, the E3.S connectors, which can be 4C or 4C plus. The picture just shows 4C. So we've got that for all of the CXL and PCI. We've got that for the OMI IO and some of the CXL PCI IO. And then for interconnect cabling, we've added I've added a near stack connector, a near stack PCI from Molex. That's just for cabling IO between the modules for interconnect. So that's a more efficient use of space, and we can get eight of these in the module design. So this is a tweak from my previous concepts. So notice that this AMD, if you look at that, with 24 OMI channels and 128 PCI channels, then you've got a total of 192. That shouldn't say. So a total of 320 transceiver lanes on this connector. So 320 IOs is what we've got, and this seems like a real possible configuration of a product. So we could connect in the E3.S. We could connect the OMIs. So if we made the OMI memory in this E3 format, then we would be able to connect that into these sockets here. So we get 2 channels per connector. So we get our 24 channels. We can connect NVMe SSDs to the PCI CXL one in the same E3.S format. We can connect NIC 3.0s in there in the 4C Plus format. We can actually directly cable out of these PCI ones if we want to cable to a remote PCI device, not actually local to the module. And we can cable between all of the using this miniature near stack connector from Molex. So that's the sort of top level change there. So so this goes back now to slides we've looked at before. But we have this fully composable compute node. By the way, I've still called it OAM HPC. I guess we should probably agree on a name. I know I think Jinshu, you came up with another name for our supercomputing, so we ought to maybe discuss that at some point. So all the connectors you can see, I've got them all in that format I just showed in the previous diagram with the 320 IOs. There's a couple of things here. By these connectors being so closely coupled to the processor, we do actually have an opportunity to maybe reduce an OMI or whatever PHY channel to 5 to 10 dB or 1 to 2 picojoules per bit. And maybe that would get us a roadmap up to 51.2 NRZ without having to go to PAM4 for low latency memory in DDR5 6400. We have an opportunity as well, potentially, and I think I've discussed this before, is to get rid of the middleman, get rid of the package, and actually make the module itself a substrate and remove that package. That would improve power and signal integrity considerably, and also help towards the bullet above. So, and again, that's some efforts, work I've been doing with the ODSA chiplet work group. So if looking at that module head on, that's what the connectors look like, including a bunch of ancillary sideband management chips and clock chips that I've planned out in here. And so this is the bottom view and this is any processor and accelerator, and I'm just showing an AMD implementation. So if we populate it with the AMD use of these, then that's the actual protocols. But we got to remember this module is going to be protocol independent. These could be all CXL PCIe. They could be, you know, they could be Gen Z. They could be NVLink. They could be, you know, whatever you want it to be for your particular processor, Ethernet, you know, etc. So this is the beauty of this agnostic hardware standard. And then now, so we said let's normalize a bit more to the E3, or we can plug E1s in here as well. We've now, this is just shown with the E3s plugged in and the stack cables plugged in. And then this one is shown with the we've just taken the CXL and PCIe connectors and actually making them fully cabled. So every PCIe IO is cabled, and only the OMI memory are actually modularized here. So again, this should look familiar to you. It's not massively different, but we want to plug this thing into the OCP OAI chassis. So these already exist from Inspur, Hive, and ZT for Gen 1 OAM. So we want to plug into here, and we can upgrade as well to the new ones that are coming out from the OAI work group for which are being upgraded to PCI Gen 5, etc. So and 1 kilowatt modules as well. So if we look at it from a chassis perspective in the same AMD module, we can configure we can cable configure the topology, and this is a fully connected example that I've done here. So this will be with the near stack cables. We can see that we can do fabric expansion out of one of the near stack cables, and likely the best way to connect the hosts would maybe with the current host connection, the host interface board as it's called. We could do with one of the 4C connectors with a cable going to a backplane connector to connect into the host interface board. So we could make this box compatible with the OAI chassis. And then you've sort of seen this one. We can re-architect that. We've got the air cooled in the water cooled, pipes going everywhere. And as you know, now we've got rid of the motherboard here. We use this module with a capillary heatsink, and then we connect it to a cold plate, and we bring the power bus bars in, and a far more efficient way to bring the power in lots of very thin copper planes in the UBB, far more cost effective. We put the two together, and there's our 8 modules populated in the actual system, ready to plug into the OAI chassis. Now, I presented this to, I think I touched on this last week on the last meeting. I did present this to the thermal, the immersion work group, and obviously this isn't showing immersion, but I discussed the potential that we could get rid of these heat sinks and actually make this into like a puddle of immersion that we dip the modules into. And so I was going to do a variant of that, and there's a number of people on the call from the thermal side that are willing to help out with this. So that's one of my primary tasks on the white paper, is to get some of these 3D models out, documented, and actually do a puddle version of how I see this concept to share to get that going on the thermal side. So here's a memory pooling server. Again, this one, I'm hoping to get some better cable diagrams of this done as well, maybe with some help of some members here, and also show it inside an OAI chassis. So for those of you that are familiar with just a bunch of flash, there are some drawers out there where you slide the drawer out and you actually replace the U.2 drives, I think they are today, with from the top. So this looks like just a bunch of flash, but you've got these very powerful processors at the bottom of 8 of them. And so the beauty here is in fact, I was presenting this to somebody else, and they said you should call it just a bunch of everything. So JB or something like that, or JBO, sorry. So I may actually steal that. I did tell the person I might steal that idea. So this looks. These modules are serviceable from the top, which would be fantastic. So storage and memory modules being serviceable, that would be a delight. And you've got these very powerful 8 kilowatts worth of modules that are directly cold plate cooled, or maybe even immersion puddle cooled is what I've called it, while the modules here on top would be air cooled. Just the numbers, it would be 8 EPYC OMI processors, 48 terabytes of OMI memory in here, up to 6 terabytes per CPU. 42 terabytes could actually be shared over the CXL.mem. That should be 48, I think. 12.3 terabytes per second of aggregate memory bandwidth in this single configuration. Pretty impressive, with a lot of compute behind it. 24 PCI Gen 5x16 E3.S NVMe SSDs in this configuration, and 512 gigabytes per second of CXL.mem external memory pooling bandwidth. So that would be put available to everybody else in other nodes in the rack or in the data center. So that's really where it's coming together really quite nicely. So I wanted to give you all an update on that. So if there's any questions, we can do that, or we can move on. Any questions from anybody?
Yeah. How about computational memory?
Say that again. Sorry.
Computational memory.
Computational memory. Yeah, like computational storage.
Exactly, but also they do computational memory. I was involved in a project with computational memory with Stanford.
Yeah, yeah. So obviously,
the CPU, the processing of data and memory is happening in the memory itself. It's not external itself.
Right. So, well, we've got computational storage, which is making its way through SNIA and NVMe. And obviously, so you can buy an SSD with like a computational storage SSD from Idetacom, for instance. you can plug it in an E3. I think it's in a U.2 format, but I think that will be readily available at some point in an E1 or an E3 format. So that would be pluggable into here. I don't tend to look at these things as computational memory, computational storage. I look at everything as I'm a 1980s guy, so this is just simply distributed computing. I think by putting buckets and saying, oh, this is specifically computational A, B, and C, I think we should start looking at this all as one distributed computing. But that's just a nit point from me on how we should be looking at this. Obviously, it's easier to get success if you just focus on storage or just focus on the memory. But I think generically we want to be thinking about this as distributed computing. But yes, so the key thing here is if these people with additional compute capability in these modules near the memory and much lower power, absolutely plug those modules in. That's what this format's all about. And so that's the chiplet world. So you go to ODSA, you say, well, I want to plug in my accelerator chiplet near my memory or in the module itself, or if you're a silicon guy and you can put memory cells and compute together in the same DRAM process, hey, great, like some of the memory companies are doing. But we don't stop any of that innovation. It's just that goes into the E3 or E1 formats and is complementary to the big iron processors or the big iron accelerators or the big iron switches. Because the big iron switches now are burning a serious amount of power. So that's the idea there. That makes sense.
So this group define interfaces between different chips.
Yeah, we're trying to define. We're trying to define the hardware, the modular, flexible, and composable hardware architecture for open high performance computing. We are not the inventors of the silicon or on a processor, accelerator, switch, or networking, or storage or memory side. We're just providing the modular building block platforms for everybody else to effectively innovate inside those modules. And then if you're a startup, you can innovate what you've got in one of these modules, knowing that you'll be able to plug it into this wider ecosystem that OCP is driving for the open hardware architecture ecosystem. So that's the key driver there. That's what we're trying to achieve.
Yeah, so defining interfaces between all these modules in the ecosystem.
Yes, that's right. But this is a big problem. Is if you look at what's out there right now, so we've got OMI, CXL on the memory side. You've got CXL on the fabric as well. You've got Ethernet, you've got InfiniBand, you've got NVLink, you've got Infinity Fabric. So you've got all of these different connections, memory type buses, fabric type buses, near memory low latency, worse latency. And we're not trying to prescribe, we're trying to make an industry standard so everything can physically connect to everything. It's when you plug one module in with another module, they have to negotiate, can they talk the same language? And so that's a sort of a sideband management thing that we would need to build into this architecture. And if they can have a common language, PCI may be the base one, then great, they communicate with that. If they talk a very efficient one, like OMI for near memory, then they both talk OMI. So that's the idea. We're just trying to standardize the physical interconnect, a bit like the PHYs in transceivers are now multi-PHYs as well, if that makes sense. And hopefully the industry will coalesce. CXL seems to be making progress there on the fabric side. With PCI support. So hopefully the industry will eventually coalesce and it won't be so difficult to plug these pieces together. But we're trying to put pieces in place so that the industry has something to coalesce around.
Very good. It is ambitious endeavor.
Well, and that's why I'm doing it in OCP. It's just it's a case of that we need collaboration across every discipline to make this happen. And we don't want this can't be driven by one of the smokestacks, because the smokestacks is they want to buy everything from them, and that doesn't promote open standards and you know and in terms of you know, support for you know, the startups of this industry that are being funded by hundreds of millions of dollars of venture capital money. They have nowhere to plug. If you know, if a customer comes along and says, I love that NVIDIA GPU, I love the AMD CPU, and I like the Intel FPGA, I want to plug the three together. Well, NVIDIA are not going to be too happy about that, nor is AMD, and nor is Intel. But it would be lovely if they could all plug together and all talk from an industry innovation perspective.
And from an innovation perspective, industry innovation perspective, it is also important to find out what companies like IBM because is doing in this area, because they do lots of research in hardware in New York lab and in Zurich lab and in other labs.
Yes, yeah. So the idea is we democratize these hardware into modular building blocks that everybody can bring their piece, their best piece in the world to, and researchers and universities and national labs and companies can plug together the best bits of many vendors.
Do we have somebody? Do we have somebody from IBM or any one of these national labs?
So IBM. Well, I'm actually the OMI OpenCAPI technical director and board advisor. So I'm actually plugged into IBM through OpenCAPI and OMI. But you know, that's just one of my consulting gigs. But I'm trying to be generic here. I'm showing the OMI one because this was an exercise I did with OMI. So that's why I'm showing OMI. But if you don't believe in OMI and you believe in CXL or you believe in Gen Z, you pick your poison. The one thing we got to get away from is parallel DDR memory, because that is just not composable in what we're trying to achieve here. So you know, in OCP again, I'm trying to build a democracy here. So I don't want to force OMI down everybody's throat. I want everyone to make a decision that OMI is a good way to go. So that's a demarcation for me personally, but yeah. So I've got connections to IBM, and I'm trying to get Open Power. Open Power wants to contribute to OCP, so I'm trying to get some of these projects going with them as well. But equally, I'm trying to convince other people. You know, we've got to get a couple of vendors, the big ones and a few small ones. If we can get us moving on this architecture concept, I think we can get some traction, and then we'll be off to the races. So that's the stage we're at. We're really at the very early stage right now. Okay.
I think you know it's a great presentation, and has a lot of wonderful idea, and I need to digest your slide later. So is it available?
Yeah, no, so this recording will be updated, so you'll be able to see the entire recording, and I'll post the slides as well.
Okay, great. Okay, thank you. I actually have a lot of questions, but
yeah, and well, if anybody wants to have a
time.
separate call, just ping me, and I'm happy to have a deeper dive if we can get you plugged in a greater or lesser way. You know, if you want to contribute. Like I say, on the thermal side, I think I attracted some things there, and Philippe has been very good offering some help, and a few others as well. So on the thermal side, because I've just stirred that up, I'm going to get as much technical information into the white paper, so the thermal guys can go away and do their simulations. So if you've got desires on plugging a particular module into this. And trying to get the ball rolling, then we can set off a set of sub work groups working on the different pieces of the white paper.
Okay, great.
So now,
Can we build a spreadsheet where we compare between various interconnects like CXL or BCI, all these interconnects, and compare between them, or this is outside the scope of this?
The interconnect one is, I guess my desire on the interconnect one is to support everybody. I don't want this to become a political shop of where we all want to drive one or the other. I want us to make sure that the pieces are in place so any fabric can talk any language, and it needs to be, we need to have some refinements in the sidebands somehow, so there is a negotiation of, we've been plugged together, we have a channel that's been plugged together, can we talk the same language? Either we can or we can't, and if we can't, the system reports it through the software and says, we've got a connection between us two modules and we can't talk to each other, we talk different languages. So that the system fails to boot, so to speak, until you've wired up a configuration that is viable. And if you've got an FPGA somewhere, they're a universal joint, so you could get an FPGA to talk one language on one port and convert it to another on the other port. But yeah, so that's the idea there. So I think where we get involved is how does the sideband management get managed at boot time to make sure that two connections are actually compatible with each other, or a connection between two devices, should I say. Does that make sense? Okay. All right.
Yeah, one more question, quick question. So the purpose of, your presentation is that's this hPC's the mission, right? Is that right?
Yeah, so effectively we're focusing on the work group is focusing on the hPC high performance computing area. Yeah, that's
Okay.
so and we started with some metrics. I mean, basically we simplify the metrics in a sense for now at least into, really we want the highest performance because that's what hPC is all about, but it's got to be at the most efficient implementation, and the lowest cost possible. Those are the sort of highest performance and most efficient, and lowest cost. And so
also, the modularity and composable.
Yes, the modularity and composability is a prerequisite, and that's a key driver. If you look at OCP's main mission, then modularity is, I think, it's number one in its mission goal.
Yeah, I love those concepts anyway. Yeah, that's the way to go, I believe.
Okay.
Again, I have a lot of great information in the slide, and I need to review and then maybe get back to you later. Okay, thank you.
Okay, that's all right. Any other questions? Okay, I'm just capturing. I think a few people jumped on, so I'm just trying to capture. Okay. All right, so if we switch gears to the white paper, we did, I think somebody might have said they did actually, here we go. So I've not looked, but we sort of, oh, there we go, direct liquid cooling. So Luca, thank you very much for popping something in there. Okay, that's good. So we have somebody kicking off, so that's great news. All right, so we'll review that. I was just wondering if we wanted to try and get some specific actions on people at all. We've only got the 10 minutes left here, and I may have jumped. We've sort of talked around the white paper. I guess the key thing I'm going to do is I may try and get some words in on the overview from the likes of this presentation to get the feel for people of the overall. And I'm because I've got some interest on the thermal side, and I've got some actions, I'll try and dump some information in the thermal side here of the current state of the module, so we maybe can get some thermal simulations on kilowatt modules, etc. I mean, for that, if people like I'm saying, if I'm spurring you off and you're thinking along like Michael, or the people that have contributed today, Hisham, if you've got some views you want to dump and discuss into this white paper, then please go ahead and do so. Like I say, there's no bad idea. So if it can get if we can start to get some subgroups going, diving into some of these details, then I think that would be tremendous. And like I say, I'll try and feed you all on this as you need information from me on this side of things. Just quickly going back, I'm just conscious of time, and I didn't want to take up too. If there's any input on the white paper, if anybody, really it's a case of we wanted to try and get some momentum here. So I'm using the white paper as the angle for us to get some momentum. Now, I guess the only topic now is on the global summits. So we've got the SC21 panel applied for, and we need to find out if we haven't heard yet whether we're going to be admitted into the supercomputing panel. So I hope so, keeping our fingers crossed. But it's I think it's about a week before that we have the OCP Global Summit. So it was really to put we want to start thinking about what do we want to do at the OCP Global Summit. Would we like to do a bunch of presentations on progress? I guess we're a little bit early here, but the opening of the call for papers is today, is the first day, and I believe it's about a month or maybe 6 weeks before the close for the call for papers happens. So if we can get some traction in some of these sections of the white paper, maybe we could do like lightning talks, a bit like the OCP Tech Week we did before, just talking about each piece of our efforts, like the thermal piece, the power piece, signal integrity piece, modularity. If people are willing or interested in doing that and saying, I'd like to put my hand up and I'd like to present, I'm thinking the lightning round approach went fantastically at the OCP Tech Week. I need to check with Archna and the gang as to what formats they're going to support, to see if we could do a bunch of lightning round presentations. But I'm thinking that might be a good way to do this, and then the experts from you lot can present what progress you've made in this work group. So does that sound okay to everybody for OCP Summit? It's in November.
Yeah, I think that sounds good. Sounds a good idea. Yeah.
Okay, good. Okay. Well, I'm going to give any other business a chance now. Is there any other business from anybody? Anybody would like to bring up any other topics that we can talk about in the last 5 or so minutes?
Can you hear me?
Yes.
Okay, it's Al Wegener.
Hey,
so I've been on the call the whole time, but for some reason on my mobile phone, I was not able to mute the mic or unmute the mic. So
right.
Do you want me to give an Anacode intro?
Yes, please do.
Okay. So Anacode is a lossless compression technology that works for any kind of data, text, integers, floating point, etc. I met Alan Cantle when he was still at Molex, and so Anacode is about ready to launch on Amazon Web Services and perhaps other clouds. So what we do is lossless compression, faster and more compression than anything out there, including gzip and zstandard. And especially for numerical data, Anacode has a different way of doing things. So this is another way to increase bandwidth, is to make the data smaller. So it's orthogonal to the physical efforts that Alan has been involved with. Thank you, Alan.
Thank you.
Back to you.
So do you have any comparison? Like, what kind of comparison efficiency you have over the existing one, and also the
Yes.
speed.
And if you'd like to send me any data, I am al@anacode.io. I live south of Santa Cruz, California, so near Silicon Valley. So anybody that wants to send me data, please do. I'm very technical, as Alan will tell you. And I think this would make a nice, Anacode would make a nice SoC IP block someday.
Mm-hmm.
From a context of this, the current effort of this work group, you would be in the silicon with the various fabric protocol communication.
Yeah.
Well, you would be the like the in-memory acceleration or the near storage acceleration type.
Yes. Now you talked about AMD EPIC and the what was the Italian name? Naples, the Naples chip. So because Anacode is scalable and block oriented, it fits very nicely with things like microservices and containers, things that are cloud software technologies. So if Anacode is massively parallel scalable compression, lossless compression, then it's very friendly to hardware as well. And that's how Alan and I were talking about it as a FPGA SoC IP block, but there's no reason why it couldn't become just an SoC IP block by itself.
Yep. Okay, thanks, Al. Thanks for the intro.
You're welcome.
Okay, on that note, we have 4 minutes left. Any more AOB? Is there anyone else new that I missed that's on the call?
Alan, for the interconnect, I think we should add the co-packaged optical that is evolving rapidly, especially now on the switch side. Basically, the next generation, I would like to say new generation of Ethernet switch will have the optical interface, the high-speed one.
Yeah, good one. You're absolutely right, Jinshui. And this actually, I mean, this is something that I've been thinking about in the background, and but is not included in this right now, except for, you know, potentially these cables could have the optics built into them, so you can go from electrical to optical very, you know, in the paddle card, especially with silicon photonics and the much lower power. But obviously there's the other angle of co-packaged optics, where you've got tremendous orders of magnitude increase in bandwidth that you're talking about. So I do have some crazy ideas on how we could potentially support co-packaged optics in this current module format. I haven't turned them into concept models yet. They're just concept models in my head. But I think that's a really, it's a bit like immersion cooling. It's like a big leap in the chiplets. You know, the immersion cooling, the chiplets, the co-packaged optics. These are all very interesting major changes in our industry, and if we can make them, they are going to be game changing. It's going to be game over for everything as is. The question is we've been predicting co-packaged optics and silicon photonics for 20 years. So, and the immersion cooling, etc. So it's a case of what can we do to get us closer to these and actually architect something that we could maybe bridge into them really effectively. So I think that's a very, very good topic, Jinshui. And we definitely need to add that to the to-do list. And I'll put a section. It's on the interconnect section, but I'll certainly I certainly think we want to pull that thread of how do we manage this transition, for sure.
Okay, yeah, because the hPC will be, I believe, will be the first one to use. Okay, in the last.
Yes,
yeah.
yes. HPC will be the first to use for sure.
Yeah,
and I'm sure what will happen, it will be the first to use it, but it'll be the first to use it, I'm sure, in a very expensive Fugaku type machine. And it's our job to say, can we make this technology, can we get ahead of it and say, we can actually put this into an industry standard low cost approach with this modularity. I think that's our drive here.
Yeah, if you look at the new Ethernet switch, that's the 400 gig and 800 gigabit Ethernet switch coming out next year. They will have the the CPO.
Right. So the switches will have it. Right. Okay. Yeah. So very good stuff. And for sure we need to add that to our to-do. So thank you for that, AOB Jinjui. On that note, it's 9 o'clock. So I think we'll call it a wrap. Thank you, everybody, and see you later.
Thank you.
Thank you.
Thank you. Bye. Have a good
Bye.
day.